Have you ever wondered how infinity could be contained in a finite space? Welcome to the intriguing world of mathematical loops. In the vast realm of mathematics, there's a fascinating concept that ties together the abstract and the concrete, the infinite and the finite. It's the concept of mathematical loops. These aren't your ordinary loops, the ones you might tie on a shoelace or the loops of a roller coaster. No, these are loops that exist purely in the abstract world of numbers and equations. Imagine, if you will, a line that stretches on forever. Its two ends never meeting. That's a concept we're familiar with. It's called infinity. But now imagine folding that line in such a way that its two ends do meet. You've just created a loop, a closed loop that contains an infinite line. It seems paradoxical, doesn't it? How can something infinite be contained within something finite? Yet that's the magic of mathematical loops. But why should we care about these loops? What relevance do they have to our lives? Well, as we'll discover in this video, these loops are not just abstract mathematical concepts. They have real-world applications, from the routing of internet data packets to the orbits of planets around the sun. They help us understand complex systems and predict their behavior. They're tools we can use to unravel the mysteries of the universe. And yet, despite their utility, mathematical loops are not without their challenges. There are still many unanswered questions about them, many mysteries yet to be solved. But that's what makes them so fascinating. They're a reminder that even in a field as logical and precise as mathematics, there's still room for wonder and discovery. So, come with us on this journey into the world of mathematical loops. Whether you're a seasoned mathematician or just a curious observer, we promise you'll find something of interest. We'll delve into this concept in a manner that makes it accessible to all, breaking down complex ideas into simple, understandable terms. Stay tuned as we unravel the mysteries of mathematical loops. Before we dive into the complex, we must first understand the simple. So, what precisely is a mathematical loop? Imagine, if you will, a racetrack. The starting point and the finishing line are one and the same. That, in essence, is a mathematical loop. It's a construct in which the end point coincides with the start point, thus creating a continuous cycle. Just like a race car that keeps going round and round, a mathematical loop isn't about reaching a final destination, but rather it emphasizes the journey, the process, the cycle. But why do we care? What significance does a mathematical loop hold? Well, the answer lies in its omnipresence. Loops, you see, are all around us. They are integral to mathematics and, by extension, to our everyday lives. Be it the orbit of planets around the sun, the cycle of seasons, or even the rhythm of our own heartbeat, they all follow a looped pattern. In mathematics, loops help us understand periodic phenomena, patterns that repeat themselves over time. They are fundamental to many branches of mathematics, including geometry, topology, and even number theory. For instance, in geometry, a circle is a perfect example of a loop. Its points are all equidistant from a center, and any path you take around it will inevitably bring you back to your starting point. Moreover, loops are not just an abstract concept confined to the realm of mathematics. They have practical applications in various fields such as computer science, physics, and engineering. In computer programming, a loop is a sequence of instructions that is continually repeated until a certain condition is met. In physics, oscillations and waves follow a loop-like pattern. So in essence, mathematical loops provide a framework to understand, model, and predict cyclical phenomena in various disciplines. They are the invisible threads that stitch together the fabric of our understanding of the world. With this foundation, we're ready to explore deeper aspects of mathematical loops. Infinity, a concept that both baffles and fascinates, but how does it relate to our loops? Let's delve into the magic of infinity and how it intertwines with the concept of loops. The idea of infinity is a mathematical concept that represents an unending quantity. It's the idea that something can keep going perpetually without end. And here's where loops come in. Loops, in essence, are an embodiment of this concept. They represent processes that can continue indefinitely, yet within a finite structure. Think of it like a racetrack. The track itself is finite, it has a clear start and end, but a car can keep going round and round indefinitely in a loop. This is a simple, tangible representation of an infinite process within a finite structure. Now let's take this a notch higher. Consider a mathematical function that repeats its values in regular intervals or cycles. This is a loop. The values may be finite, but the process can continue indefinitely as long as we want it to. It's like a never-ending journey on a circular path. The beauty of loops is that they allow us to grapple with the concept of infinity in a tangible way. Infinity is, after all, a difficult concept to wrap our minds around. It's not something we can easily visualize or physically experience, but through loops we can see and feel the essence of infinity. We can observe how a process can continue endlessly, how it can keep repeating without any signs of stopping. This is the magic of infinity as expressed through loops. It's a fascinating intersection of the abstract and the concrete, the infinite and the finite. It's a testament to the power of mathematics to express and explore concepts that go beyond our everyday experiences and perceptions. Indeed, loops provide a tangible way to grapple with the infinite. Now that we understand the basics, let's delve into how loops manifest in various mathematical contexts. One way loops come into play in mathematics is through iteration. This is a process of repeating a set of steps over and over again, each time applying the result of the previous step. A simple example of this is the multiplication process. If we want to multiply 5 by 3, we can think of this as adding 5 to itself 3 times. Here, the loop is the repeated action of addition. Next, we have recursion. This is a more complex form of iteration where the output of a function is used as the input for the next application of the same function. If you've ever seen a set of Russian dolls, where each doll contains another smaller doll inside, you've got a pretty good idea of how recursion works. Each doll represents a recursive step, with the smallest doll being the base case that ends the recursion. Then we have fractals. A fractal is a geometric shape that can be split into parts, each of which is a smaller copy of the whole. This is a beautiful example of loops in mathematics. If you zoom into a fractal, you'll see the same pattern repeating over and over again, seemingly without end. This is because fractals are defined by recursive equations, with each iteration of the equation producing a smaller copy of the previous shape. And finally, there's the concept of cyclical sequences in number theory. This involves sequences of numbers that eventually repeat, creating a loop. For instance, the decimal representation of the fraction 1/3 is 0.333, with the 3 repeating indefinitely. These examples show the diverse ways loops are employed in mathematics. Whether it's iteration, recursion, fractals, or cyclical sequences, loops add a layer of complexity and beauty to the world of mathematics. So the next time you come across a loop, remember, it's not just a simple circle, it's a mathematical journey. Math isn't just about abstract concepts, it's also about practical applications. How do mathematical loops apply to our daily life? Well, let's dive into it. One of the most common places we find mathematical loops is in computer programming. Here, loops are used to execute a block of code repeatedly until a certain condition is met. For instance, a social media app might use a loop to display all your friends' posts, one after the other. The loop starts at the first post and continues until there are no more posts to display. Quite handy, isn't it? But it's not just the digital world that benefits from loops. The field of physics is rife with them too. Take, for example, the concept of a feedback loop in systems theory. This is a process where the output of a system is used as its input. Think about your home's thermostat. When the temperature drops below a certain point, the heating kicks in. Once the desired temperature is reached, the heating switches off. This cycle or loop continues to maintain the temperature. Mathematical loops also play a vital role in engineering. In structural engineering, loops are used in the iterative design process. Engineers may start with a basic design, then continually revise and improve it using feedback from each iteration to inform the next one. This loop continues until the design meets all necessary criteria. Even in our everyday lives, we can find examples of loops. Consider your daily routine. You wake up, go about your day, and eventually go to sleep, only to repeat the process the next day. This is a simple example of a loop, but it's a loop nonetheless. So whether it's the repetitive actions in a computer program, the cyclical processes in physics, the iterative design in engineering, or even our daily routines, mathematical loops are everywhere. They help us understand and manage the world around us, making complex systems and processes more predictable and manageable. As we can see, mathematical loops aren't just theoretical, they have practical uses that impact our daily lives. There's a certain beauty to mathematical loops. They're not just about numbers and equations, but also about aesthetics and symmetry. The beauty of mathematical loops is in their simplicity, their elegance. They embody the principle that within repetition there is variation, and within variation there is pattern. The loop, in its most basic form, is a circle, a symbol of unity, wholeness, and infinity. But mathematical loops are not just circles, they can be spirals, helixes, fractals, and more. Each one is a dance of numbers and symbols, a ballet of logic and pattern, a symphony of symmetry and balance. Just as a painter uses brush strokes to create a masterpiece, a mathematician uses loops to unfold the universe's secrets. It's a language of patterns, a lexicon of loops, an alphabet of algorithms. It's the poetry of precision, the art of accuracy, the beauty of balance. Each loop is a verse, each iteration a word, each repetition a rhythm. Imagine, if you will, a loop as a piece of music. Each iteration is a note, and as the loop progresses, the notes join together to form a melody. This melody is not just audible, but visible and tangible. It's the melody of the universe, the song of the stars, the rhythm of reality. Let's not forget how loops have influenced art and design. The swirling patterns of Vincent van Gogh's Starry Night, the intricate designs of Islamic art, the mesmerizing mandalas of Buddhist tradition all owe their beauty to loops. Even in nature, we see loops everywhere, from the spirals of galaxies to the patterns on a seashell. Mathematical loops, then, are more than just tools for solving complex problems. They're a way of seeing the world, a lens through which we can appreciate the inherent beauty and symmetry of the universe. They are a testament to the underlying order and harmony of existence. Indeed, the beauty of mathematical loops extends beyond the realm of mathematics. Mathematical loops, while fascinating, also present challenges and mysteries. What are some of these? Well, let's delve into the enigmatic world of mathematical loops. One of the most challenging aspects lies in the realm of infinite loops. Deciphering the behavior of these loops, especially when they involve complex calculations or algorithms, can be a daunting task. The difficulty escalates exponentially when we try to predict the end state of these loops, if there is one, or determine their impact on the systems they are part of. The mystery deepens with something known as the halting problem. This conundrum is about whether we can predict with certainty that a given loop or program will eventually stop or continue indefinitely. Proposed by the brilliant mind of Alan Turing in the early 20th century, this problem remains unsolved to this day, adding an extra layer of intrigue to the study of mathematical loops. And then there's the challenge of computational complexity. The time it takes to complete a loop, particularly in computer science, can vary widely depending on the size of the data set the loop is working with. This issue raises questions about efficiency, optimization, and how we can improve the speed and performance of loops. One more mystery we encounter is the paradox of self-reference, often illustrated by the famous "this statement is false" paradox. This loop of logic, where each part refers back to the other, creates an endless cycle that is both puzzling and fascinating. Despite these challenges and mysteries, or perhaps because of them, mathematical loops continue to intrigue us. They invite us to explore, to question, to solve. They push the boundaries of our understanding and encourage us to delve deeper, to unravel the complexities and seek the solutions. The challenges and mysteries of mathematical loops make them an even more captivating topic. We've been on a fascinating journey through the world of mathematical loops. Let's recap what we've learned. We started our adventure by delving into the intrigue of mathematical loops. We discovered that these aren't just simple shapes we see on paper, but they're representations of a concept that's at the heart of mathematics: infinity. As we moved forward, we took the time to understand the basics. We learned what a loop is in mathematical terms and how it can be represented in different forms. We found out that a loop, in essence, is a path that starts and ends at the same point, with no breaks in between. From there, we turned our attention to the magic of infinity. We explored how mathematical loops, with their never-ending cycle, are a perfect embodiment of the concept of infinity. We saw how this one simple shape can encapsulate an idea as vast and complex as infinity. Then we delved into the specific role of loops in mathematics. We discovered how these loops help in solving complex problems, making calculations more efficient and understanding patterns and sequences. We also learned about the different types of loops and how they each serve a unique purpose in the world of mathematics. Our journey then took us to the real-world applications of mathematical loops. We saw how these loops aren't just theoretical constructs, but practical tools that have wide-ranging applications in fields as diverse as computer science, physics, and even art. We also took a moment to appreciate the beauty of loops. We saw how they embody a certain elegance and symmetry, making them not just mathematical tools, but also objects of aesthetic appeal. Lastly, we faced the challenges and mysteries surrounding mathematical loops. We discussed some of the unsolved problems and the ongoing research in this fascinating field. Next time you see a loop, remember it's not just a simple shape, but a representation of infinity, a tool in mathematics and a source of beauty and mystery. Thank you for joining this intriguing exploration into mathematical loops.